let's talk to Peter. Peter, you look great. What is that scarlet tunic?
Well, it's very appropriate that this is about heat, because I want to tell you right now, the Calgary Flames are red hot. This is the first time that our hockey team has made the second round of the playoffs in 11 years, and the city is going crazy. I don't know if you know this about Canadians, but a good example of how hockey crazy we are. Why do Canadians... Sorry.
Well, okay, and with that hot topic as an introduction, by the way, on the issue of sports teams, as you can see, we are in beautiful sunny Oregon, Portland, Oregon, where we didn't have a good result last night with the Blazers and the Grizzlies, and so we're happy for you, but we have other emotions going on as well. Won't go into it. So, Peter, you are May-Ruben, and you've got this dual fluid ejector. John, what did you first think about when you heard about dual fluid ejectors, and what was your notion? What are you expecting to hear here?
Well, it sounds complicated, so I'm eager to learn more about it and hear about how this works.
Neil, how about you?
It is a terrible name. Obviously, we had our scientists on board before we had any marketing people.
That's right.
Well, if you were a marketing person, what would you call it?
Oh gosh, that's a good question. I'll come back to you on that one.
Okay,
Neil, your opening questions for Peter would be.
As always, it's all about the money, right? Ultimately, the economics and the economics all around again. The space required, the energy input, and the capital cost.
Exactly.
Okay. All right. Well, Peter, why don't we get out of your way, and we'll bring your slides up, and you can take over.
Okay. All right, so this is obviously all about harvesting waste heat. That is the theme today. And just to introduce the company, we are a development company. We are the sole purpose of bringing this technology to the market. And we are a small but highly qualified. It's not immodest to say that we're world leaders because it's a very small field. We may be one of the very, very few working on this. We do have a strong collaboration team. DuPont has been involved in the fluid development, University of Calgary in the fluid dynamics. We're doing a lot of exciting stuff there. Gas Technology Institute, the gas utilities industry really wants a cost-effective, scalable gas-burning heat pump, so they like this opportunity. And we're working with an OEM now in Canada to build the first prototype and a CHP company that we will be bundling this with. So waste heat obviously is a vast resource. Over 50% of the energy consumed in America is lost as waste heat, and very little of that is tapped. And so the question is why? And it comes back to economics, finding value. And so what are the ways that we can use waste heat? Obviously, if you can use it at a recovered temperature, you can use a fairly simple heat exchanger. But even those are expensive, and you have to have a return on that lower value, lower temperature heat as pre-warming or something like to that in that order. There's other things that you can do, however, and that would be including raising it to a higher temperature. So if you need to re-inject it for process heat, you can raise it with an electric heat pump or a thermal heat pump. And so in these cases, we can also use waste heat as the source for the upgrading to that higher temperature. But there's another way to use the waste heat, and that is as the driver rather than the source. And in this case, you can only use a thermal heat pump to produce the freezing or cooling that you're looking for. So won't go through this too detailed, but thermal heat pumps can be used for cooling, heating, and the separation. The separation is really kind of a combination of both sometimes, such as distillation or drying. Separation technologies represent 22% of all the industrial energy in the United States, so it's not small. But most people think of the cooling applications for heat pumps. And of course, there's a number of sources and also a number of drivers if you can use a hybrid with natural gas as the driver. Electrical heat pump, your heat sources are only that, just a source, and you're restricted to these two applications. So one of the things, though, that's kind of sad is that there seems to be a consensus among various government and institutions that it's just not working well enough. Current technologies are not doing a good enough job, and this was from a waste heat opportunities study done by the DOE, and basically they are saying that for low temperature heat recoveries, we need completely different approaches in order to tap this potential. The same thing was really echoed by the Electric Producers Research Institute. In their survey, they said there's only about 3,000 electrical heat pumps in the United States, and most of those are used for drying timber, very small inroads. And again, they say new technologies are going to be required to expand this. Well, it's pretty easy to take a look at some of the existing technologies and see what the challenges are. For electric heat pumps, it's the cost of the electrical drive that you're substituting for the thermal energy. So here's just a made-up case where you need 6,000 MMBTU of output for a dryer, for whatever purpose. And you can get that through direct fired, which they often do with agriculture, etc. And this is your input required, and at this cost, you're going to spend about $22,000. Now, an electric heat pump with a COP of 6, obviously your input is at 6. The trouble is your cost of that fuel input is so much higher. You get a fairly anemic cost savings. Great energy savings, low cost savings. When we start talking about a thermally driven heat pump, even if we only had a COP of 2, which is fairly easy for us to realize, cutting that fuel in half when you're apples to apples represents about a 57% savings. So there is the problem for electric heat pumps and their deployment. When you talk about absorption chillers, there's a couple of challenges, and they're a little bit interrelated. One of them is that there are not a great number of small absorption chillers. Most of the major manufacturers, in fact, do not offer lines below 100 refrigerator tons. And that may be a great size for a lot of the people in the audience. But certainly for commercial opportunities, commercial buildings, but also for industry. And this, another DOE study, they said that the greatest potential areas that are not being serviced for CHP cooling are in the 0 to 50 and the 50 to 100 tons. It's under the 100-ton mark that has the greatest opportunity, and it's not well served, and that is an area that we will be targeting in our first product lines. Now, the reason it's not well served, again, ties back into number 2, they're expensive. The graph on the left shows that as you move from the right-hand side, which is a 1,000-ton chiller, as you move down in capacity, the cost per refrigerator ton begins to rise. And it begins to rise like a hockey stick as you get down near 100 refrigerator tons. So here's single effect, double effect. The lower dark line is electrical chillers. We are going to track very closely to electrical chillers. We might be a little bit more expensive from the costing we've done, but we are have the same components. We are a vapor compression with the same basic components. So it will rise, but it will not rise as rapidly as absorption chillers. And here's a costing exercise we did with the, over here, with the, trying to get my pointer to work. That doesn't matter. On the right, we see costing exercise we did with gas technologies, trying to compare components with an electrical air conditioner, and we were about 15%, 20% more expensive when you added things and took things away. But for that scale, we're a quarter of the cost of an absorption chiller. And so we have a capital advantage, and we think we also have an efficiency advantage. Single effect, which is what is used most commonly in waste heat situations, is 0.5 to 0.6. We're going to be in the range of 1 to 1.2, maybe even a little higher. one of the strengths of the earlier presenter was with using ammonia. They can get into that freezing temperatures, which most manufacturers with lithium bromide do not go. It is possible with ejectors to operate within any temperature range, but it may have to be done in stages. And complexity. There are more components to a absorption chillers. So they're not very popular with some people, as in this quote from Dresser-Rand, but as was pointed out at the beginning, there's been good advances recently in control systems to avoid some of the pitfalls that really plagued them in the past. Well, so here is our solution. Now, this is what an ejector refrigeration system is based on. What we do is replace a complex motor with all the brushes and windings with a boiler. We replace some type of mechanical compressor with all of its bearings and seals with an ejector. And within these components, there are no moving parts. Yes, we still have to have pumps for moving cold air around, or fans for moving cold air around, and we do need a pump to put the feed back into the boiler. But all in all, the beauty of this system is it's reliable because it's simple. So here is good. Thank you, sir. Right on time. Here's an example of an ejector, and it's a bit like a Bernoulli. So there's a high, from the left, what you see entering is a high steam, a supersonic jet, and it sucks up the refrigerant fluid, in this case the blue, and they entrain, and then they begin to stack up and compress. And so as they enter with a low pressure and high pressure, they emerge with medium pressure, and that way they actually serve and work as a compressor. Okay, so if we can jump back in to, there we go. Now, the beauty of this is kind of a back to the future. It is an old technology. It was discovered in America in 1910, and that is the way that they used to air condition Pullman cars on the railroads. They made ice plants when there was in areas where they had no electricity or low electricity, and of course they could chill factories. Back then they were scaled from as small as a train car to as large as what you see here. That looks like a pedestrian walkway. Is actually a giant ejector, and so they are quite capable of operating over a number of ranges. Here's an example of where this technology was rediscovered and improved in the late 1980s. The Soviet Academy of Refrigeration experimented with using two fluids, and they ended up with a nice pilot plant that ran for a year, providing cooling for castings and air conditioning, but it was all dismantled with the fall of the Soviet Union, and the people involved were scattered. They ended up in South Korea working for LG until recently. We, in 2010, began this, as did the group that was working on the Soviet one, and we are able to accomplish about a 300 to 500% increase over the prior efficiencies, making this technology viable again. So here's the basic 101. You have a compressor, you have a condenser to remove the heat, turn it back into a liquid, and then in the evaporator goes from liquid to gas, absorbing heat from what's around it. And this cycle is repeated, driven by the compressor. Our cycle is exactly the same, and this is what we call a reverse Rankine. The problem comes when you begin to look at the drive cycle. And now you have two different cycles. On the drive cycle, it's a classic steam engine, a forward Rankine cycle. And the principles are entirely opposite. In the evaporator, when you go from liquid to gas, you want to be a big sponge and absorb a great deal of energy. But when in the boiler, to make it go from liquid to gas, you do not want to have to put in a lot of energy, because that costs you. That's your drive energy. So that's made for a bad compromise in inefficiencies. A binary fluid ejector has two different fluids optimized for the two cycles that separate in the fractionating condenser. And so now we can have a great sponge in the refrigerator and a measly little sponge in the boiler in terms of change it from liquid to gas. We're doing some interesting stuff on nozzles. No one has ever applied the kind of rigor of that we are doing CFD modeling, fluid dynamic studies on ejectors. So we're entering in some interesting new area there I'm not going to go into right now. But in terms of applications, for us, we like bundling this with a CHP systems. Bring your waste heat with you. A lot of opportunities for CHP are undershoot because the facility can't make full use of the waste heat. Adding a cost-effective cooling component makes a big difference in those economics. And to date, if you've added an absorption chiller to a CHP system, you've actually dragged the economics down in terms of payout because of the cost and low return on particularly smaller absorption chillers under 100 refrigerator tons. Heat pump drying, GTI recently won a fairly large grant to do a pilot plant in Southern California for their proprietary drum dryer, and they want to incorporate a BFE heat pump to capture waste heat from that dryer and recycle it back in. This is like the electric heat pumps used for timber drying, only far more cost effectively. So in terms of development, we have spent a lot of time in the science doing computational fluid dynamic modeling. We have validated with a smaller test rig. We've built a full-scale test rig down below, and beginning this year, by the end of this year, we're working with Ecologics, a manufacturer in the East, to build the first operating fully functioning system, and that will be 2 refrigerator tons, just kind of a household scale. But once we get that going, immediately in 2016, we'll be building our alpha commercial prototype that will be either 10 or 20 refrigerator tons. We're kind of leaning towards the 20 refrigerator ton size. And a beta model in 2017. We'd like to actually be getting that in the field, and hopefully a full rollout in 2018. So that's where we are. I wish we could ship you something today, but what we are able to do is what we're looking at doing is the platform that we are using for the CHP, we can begin to market this in advance of when our cooling system, because as a CHP system, it's an excellent system that has good standalone economics, and it is all ready for retrofit when we have the cooling component to market ready to ship. So sometime in the next while, we'll actually be undertaking CHP modeling with the full CCHP integrated controls to follow. So that's about the end of my presentation. And obviously, what would be great for us at this point, we would love to find some strategic partners. We want to work with somebody and define a site, define an application that is a good application for us so that we can develop our first prototypes with a targeted scope. And so anyone that's interested, please please contact us. We'd like to chat.
Well, great. So we're open for questions, and let's invite our panel to join us again. I think there is a question. Oh, maybe that was, I think that was for the last presenter. So, John, you were first up. What questions have you got for Peter?
Well, so Peter, you said you're looking for, I guess, development partners. What sort of, do you have a sense for what sort of process or what sort of partner, and what would be, I guess, I'll be blunt, what's in it for the partner if they want to bring on this new technology?
Well, obviously, we think that the economics will be very good, and so being an early adapter gives a jump on your competition in terms of being able to reduce your operating costs. We have had some inquiries from one company that said they would like to get involved, but they wanted to be able to have an exclusive in their sector. And that's an interesting, and that's something we need to discuss and see if that makes sense for us. But at this point, the advantage really is just to be an early adopter, and we would be giving a very favorable installation rate to get this done.
Okay.
That sounds like an advantage. Neil, question? Oh.
You're muted, Neil.
Once again, Neil, we're muted.
It's the computer and the phone. I should keep them together. Space requirements. Do we have any idea yet whether we're going to be more like mechanical refrigeration or more like absorption? Or
smaller than absorption. One of the considerations, of course, is your heat exchanger size. And if we have twice the efficiency of a single effect, we will have a much smaller condenser requirement. We're not expelling as much heat. The other components are quite small. The ejector is extremely small, so smaller than a comparable motor and compressor.
And now, in terms of requirements for utilities, cooling water and the like, comparable to absorption, less, more?
Well, in terms of cooling water, like electromechanical systems, you're more efficient if you are water cooled, but we would have a better opportunity to be air cooled than absorption chillers. We believe that we can do a better job of air rejection. It's at a cost penalty. You're less efficient. You need much larger condenser.
Sure,
but more feasible than with an absorption chiller air cooled.
But doable, and therefore no water use.
Is doable without a water use, yeah.
So, Peter, do I understand you can do freezing? You just have to do a kind of a multi-stage?
Yeah, there's the Ukrainian group is with all of the trouble in the Ukraine. They would like to join us. We're trying to merge them into our company and have applied for immigration visas for them to come to Canada. They are actually much more interested in cryogenics, and they believe they can get to minus 250 degrees with a 4-stage of ejectors. And the advantage of ejectors in very cold temperatures is there are no moving parts, and so you don't have troubles with lubricants freezing up or solidifying and so on. But frankly, it's not a field that we have looked at yet. We would like to add their capacity to ours in the near future.
I've got a question for you, Peter, and this is in my capacity as a layperson. I'm not an expert in these fields, but I noted in earlier remarks offline you made reference to distillation as a side benefit, a side output. So I'm thinking there's this drought in California, and food processors in California may have to maintain their production levels using 25% less water. So is there some amazing method of getting all the benefits and adding on cleaning up water for reuse at the same time? Is that something that could even be discussed?
Skip, absolutely. In our mind, the best application, the best match for our technology is distillation, to distill water and recondense it. Whether it's desalinization or remediation of wastewater, and without taking a lot of time going to, but we're not a very strong compressor. I mean, we have great advantages. Of course, we have some disadvantages compared to a positive displacement piston. When the temperatures are closer together, then we run just like a banshee. We're really good. And when you are distilling water, you need to just operate a couple of degrees either side of the condensation point. And so we can be very cost effective. We can use waste heat to distill water, capture that heat, vapor, bring it around on the cold side and condense it, and quite scalable. So we have been taken down a path where we've been invited by Market Opportunity to look at space cooling and CCHP. We have people interested in that. personally, I would like to. I'd be thrilled if someone out there said, "Peter, we want to partner up with you, and we want a water solution," because that's where we should be.
Well, so if we find ourselves doing another innovation showcase on the subject of water remediation or water reuse, either at the front end of the food processing or within the process, would you be willing to come back and talk to us?
I would love to.
So, Peter, quick question. What are the two working fluids? It's a binary fluid. What are the two fluids?
Okay, good question. We have identified a pair of fluids which can only be used in industrial settings. It goes like ammonia. It goes to safety. One of them is inert. It's chloroiodomethane as the dry fluid. The other one, however, is acetone. Quite common, quite inexpensive, is the refrigerant, but it's flammable. It's slightly more flammable than is allowed under current standards for domestic or commercial refrigerants. It's not terribly flammable, but it is too flammable without changing the building codes. It'd be good in an industrial setting. It has about a 20% higher COP. The other fluid is from DuPont, and they're fabulous. They're non-toxic, non-flammable, benign. They're not quite as high as COP, but the numbers we talked about, we expect to be able to do a COP of 1, where absorption chiller would be in that 0.6 range.
Okay, thank you.
And they're proprietary.
So, gentlemen on the panel, we have a couple minutes. We're ahead of schedule. Thank you, Peter, for making us early. Let's revisit this disaster story thing. And this is, Peter, stick around. This is for anybody. What's the biggest disaster story in absorption chillers or waste heat that you've ever seen, and what was the cause of the disaster?
I'll start. The cause of the disaster is almost always the provider of the waste heat overestimating the waste heat. Then nothing works, right? They want a 2,000-ton chiller, so they make up the waste heat that they need, and they don't have it.
Did they lie to themselves? Did they deceive themselves, or was the instrumentation off, or how did it happen?
Usually they just deceive themselves to make the economics work.
Oh. So you're a consultant. Your job is to help people not do that. Are you able to help people not do that?
Sometimes.
John, what's the biggest disaster story? Have you seen one?
So I haven't seen so much, but I have heard of, and maybe that's something that the next presenter can talk about. Systems basically breaking up or freezing. So basically, the lithium bromide being taken out of temperature range and some adverse effects of that. So
I think Thermax actually would have something to say about that. How about success stories? Oh, go ahead. Sorry.
We used to see a lot more of that, and the control technologies on the machines today prevent that. Mm-hmm. It was not uncommon to walk into a machine room and see a tech on his belly with a torch trying to make the thing work. But I haven't seen that in a while. On a new machine, you still see it on the old ones.
Success stories. What's the common thread to success stories? What makes it work out?
Somebody getting the heat balance right. Most of the success I've had with absorption is making gas turbines perform better in the summertime.
You were a baseball coach earlier? Just fundamentals, huh?
No.
But you could have been.
But it really is. I mean, because it's simple process. So they have limits, and you can't really push beyond them, or you fail.
Excellent.